Okay, y'all, I want to give us one more example. This is number 19 from page 272, and this is in your homework. So this tends to be one of the more confusing problems, so let's go ahead and go over it, and let's talk about how we solve this. I feel like if you can solve this one, you're pretty good for the section. Now let's read it. Number 19. Postal regulations specify that a parcel sent by parcel post, package sent in the mail, may have a combined length and girth, where girth is distance around, not exceeding 100 inches. If a rectangular package has a square cross-section, find the dimensions of the package with the largest volume that may be sent through the mail. So, yet again, I've gone ahead and summarized the problem right here. Here's our stipulation on the length and the width around. It can only be 100 inches. And then yet again, we're trying to find the dimensions. So highlight that in green real quick. If I can find my green. Now we'll do blue. So we're trying to find the dimensions that lead to a max volume. Now in this case, it really does help to get a good picture of the problem. So let's talk about that. Since we're talking about a rectangular package with a square cross-section, which I went ahead and just said square base, I guess the picture is going to look something like this. Forgive my art skills. Not too bad for a Tuesday afternoon. So, once we're here, since we're looking for dimensions, it's going to be helpful for us to actually go ahead and name some dimensions. For instance, let's go ahead and call this side right here length. Two more sides I can label. We'll call this a W right here. And since we have a square base, we can go ahead and say that even this side is W. So label your pictures, give a name to what you're looking for. The reason I chose length instead of height right here is because it correlates to what we know about the stipulations. It can only be 100 all the way around and tall. Okay, next step. So step 1, summarize the problem. Step 2, look at what you're after. Step 3, and go ahead and draw a picture. Step 3 will be, hey, let's find the function that we're trying to maximize. And here we're trying to maximize volume. Volume better be, in this case, length times width times width. Or, better said, length times W squared. Now, remember, since we're trying to maximize this function, we're going to go ahead and try to derive this guy. However, we run into an issue. We have more than one variable. We don't have those tools yet. So this is where this piece of information right here is going to come in. We need to use this information to make this thing one variable so we can derive it, since we're trying to find the max volume. So, from here, what we can do with this is try to use this information to sub in for one of these variables, to get in the language of just one variable. This information, I guess, translates to 100 is the maximum combined distance of the length and the width around. And the length around, excuse me. So 100 better be L, the total length, plus the girth of it, or the distance around, which ends up being 4W. W, 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 and W. From here, I'm going to go ahead and solve out for L. And the reason for it is I'm going to sub in right here. Since W is a little bit more complicated, I'm going to go ahead and try to sub in for L here. That being said, when we solve, we can see that L better equal to subtracting over 100 minus 4W. And this is a good bit of information to have our hands on, because we can now take that and come right up there with it. So volume better actually be equal to, subbing in for L, 100 minus 4W, all times W squared. Or, simplifying out, volume better equal 100 W squared minus 4W cubed. Now don't get lost in the details. Remember, the goal is to actually figure out where this thing is maximized at. That's why we're targeting this. In order to figure out where it's a maximum, we're just going to go ahead and apply a 3.1 or a 3.2 process. Either way, we got to find the derivative in order to find a max. V prime in this case better be 200W minus 12W squared. Now maximums only occur at critical values, so my next step is to find the critical values. Now I'm going to factor this a little bit to make it look nicer. If you see, we can actually factor out a 4 from each of these and a W as well. So what we end up factoring out is a 4W, and what's left over is a 50 minus 3W. From here, since we have one side equal to 0 and two things multiplying, we can set each factor equal to 0. So 4W equals 0, 50 minus 3W equals 0. Now this one right here, if I were to solve it out, I just get that W equals 0. Now that's not really going to lead us to anything because we don't want that for this situation. We wouldn't want the base to be 0. So in this case, I don't really care about this spot, that measurement. That's where we got to use our real world brain. Over here, however, solving for W, what I'd end up with is 50 over 3. Which, that's a completely valid situation. So I'm going to go ahead and hold on to this. That's a critical value. Now we need it to be where a max happens at, so we do have to test it, especially since we're working with something like this now. I'm going to test it through the second derivative up here, so if I derive it again, what I'll end up with is just 200 minus 24W and then through the second derivative test, I'm going to go ahead and plug in this critical value. Now if I get a negative number, I get a concave down function at that point, meaning it's a maximum. So plug in 50 over 3. That better equal, apologize for kind of shifting, 200 minus 24 times 50 over 3, or just 200 minus 400, or negative 200. So that means, since I'm negative less than 0, that means I'm concave down, which means I'm a max. So this point really does check out for me. Now since I'm asking for dimensions, and I have W, all I need to do is solve for L and the problem's over. So, W equals 50 over 3. Don't forget your labels, inches. And L better equal to, hey, let's plug it in over here. L better be 100 minus 4 times 50 over 3, or just 100 over 3 inches. Now remember the big picture of what's going on. First off, read through the problem. Get all your information down. Second off, try to draw a good picture and realize what you're after. Give the thing you're after a name. Make it less mysterious. Third, try to figure out what we're maximizing because that's going to be our lead into what we're solving for. We're maximizing volume here, so we made a volume function. It wasn't in its most simple form right away. So what we did is we did some algebra, used this information to get it to a point where I could derive this since we're trying to find a maximum, and then we found our critical values and did the whole 3.1, 3.2 process. And that led us to our answer over here. So, hope these two examples helped. Yeah, go get them.